All right, so we have one last type of reaction to add to our section 2 notes for chapter 8, and it's the combustion type reactions. So this is just a reaction where a substance combines with oxygen, releasing large amounts of energy. These reactions are fairly nice because they're always the same products for the most part, but also they can be some of the most challenging to balance. So it depends on the context, it depends on the example, but our burning of hydrocarbons is going to be the first one. And this should be somewhat familiar because it kind of looks like respiration from biology, where you burn glucose and you get certain products. So anytime I burn any carbon molecule, this molecule is actually a propane, which you should be familiar with. Anytime I burn a carbon containing molecule, I'm always going to end up making the same kinds of products, right? The first one being a carbon with an oxygen, I'm going to make a carbon dioxide. And then since this also has hydrogens in it, I need another stable product. And hydrogen and oxygen typically make water as a stable byproduct. So those are my two products for this reaction. I'm also going to have some energy that's going to be released as a part of this reaction, but that's not really that big of a deal because that's not an actual product and I don't need to balance that, right? In terms of it's not a physical thing, it's just energy that's released. So I have my reactants, my products, I just need to balance it appropriately. So in order to do that, I need to check on my carbons, my hydrogens, my oxygens, but I actually almost always do hydrogens first. Right, so the first thing I'm going to do is I'm going to, with this 8 hydrogens over here, I'm going to make sure that I have 4 waters. That's going to give me 8 hydrogens total. And if I see that that number, this coefficient in front of the water, is even, then this is going to work out pretty nice, right? Because this is one of those situations where water has an odd number of oxygens in it. So, and on the left, all I have is a diatomic oxygen. That means no matter what, if you have an odd number of waters, you're going to not have much fun doing this. So for this example, it should be pretty easy, but if I do another example, it might be a little bit more difficult. But since I have 8 hydrogens on both sides, and I'm also going to need 3 carbons on both sides, that means that on the right, I actually have 3 times 2 is 6, and then 4 times 1 is 4, so I have 10 oxygens total, which means I need 5 diatomic oxygens on the left. Otherwise, if I just change it up slightly, things might end up different. So this is actually a butane, right, which is found in lighters, although you guys aren't really supposed to be using those things because those are for cigarettes, but C4H10 molecule is going to combine with oxygen, and I'm going to make the exact same products from before. I still make carbon dioxide. I still make water. I still release a certain amount of energy. But this time it balances differently. Again, do your hydrogens first. If I have 5 waters over here, I know that this is not going to work out nicely, right? So right away, I'm going to know that since that's at 5, I better make this whole thing double, right? I need to have a 2 in front of that butane, and I need to change this 5 to a 10 for my waters, because then I'll have an even number of oxygens on both sides, and I should be able to balance appropriately. And so always check your waters first. But since I have 2 butanes, I also have 8 carbons, so I need 8 carbon dioxides. And again, when I'm multiplying 8 times 2, I get 16 for oxygens in that carbon dioxide. And I have 10 waters, so that gives me 10 oxygens. So that should be 26 oxygens total. So then when I'm balancing, I need 13 diatomic oxygens to give me 26 on both sides. Right? If I didn't double everything, I would have had to have a fractional or decimal amount in front of this diatomic oxygen, and that doesn't work. So I have to double everything. But you're always going to know when to double it. If there's an odd number of waters, you have to make it even. You have to double everything else. Right? So I don't have to just burn hydrocarbons. I can burn just hydrogen. Right? And this one is fairly simple, and we've actually done this already, but hydrogen and oxygen make a fairly familiar stable product. I'm just going to make a water here. I'm not going to make a carbon dioxide because there was no carbon to make the carbon dioxide. So all you have to do is combine whatever elements are given with oxygen to make stable products. So carbon dioxide and water before, now it's just water. But this balances by putting a 2 here, 2 waters, so I have 2 oxygens on both sides. And then I need a 2 over here to give me 4 hydrogens on both sides. Again, this would release energy as well, obviously, but that byproduct is not necessary in this context because I just don't need to balance it. But that's how I know that a reaction has occurred again, because you're going to feel that energy coming out. Right? You might even see that energy coming out. Again, these would be flames, fires. You'd be able to tell that a reaction was happening. My final example here would be any other kind of oxidation. Right? I can pretty much mix oxygen with about anything. It's not always considered a combustion because you have to release that large amount of energy to call it a combustion. But there are other examples that will fall into this. But they typically also fall under a different category. So I can take magnesium and I can burn it in the presence of oxygen. Right, so I'll show this to you in class, when I come back tomorrow. But when I combine the magnesium and oxygen, I'm just going to make a stable product. It should make sense to you that I'm just going to make a magnesium oxide, which is a 1-to-1. Remember, oxide has a -2, magnesium a +2, so this should be fine. I'm going to need 2 magnesium oxides because that gives me 2 oxygens on both sides. Then I'm going to need 2 magnesiums at the very beginning to get this all balanced. But again, there should be a significant amount of energy released for this to be considered combustion. But this is also something that we already talked about, right? These last 2 examples, that burning of hydrogen gas and that creation of magnesium oxide, those were both synthesis reactions. Right? In both, I actually made one product, that water or that magnesium oxide. So they were synthesis reactions. You combined those elements to make a compound. They just happen to also be combustion reactions because lots of energy was released. Right? So oxygen does need to be involved in a combustion reaction, but as long as there's lots of energy released, it's going to be considered a combustion. The last 2 examples, again, look like synthesis, but they're also combustion, so they can be under both categories, both labels, whereas the first 2 are combustion only, right? Burning that propane or butane, right? Making carbon dioxide and water, those are combustions, not synthesis, because they made multiple products. All right, so that should cover it. You just need to work on your worksheet.